Welcome back to the third and final FRQ that I need to do and explain for Mr. Papico's class in order to get a high B or a low A. In this video, I will be discussing the third FRQ in this packet. It is a 2019 AP Physics 1 free response question, 12 points, suggested time 25 minutes. In this video, I will read the problem as always, read every part of it, then I will discuss the science you need to learn in order to be able to solve it. I will go on an in-depth description of that, and then I will go about applying that science that I have just elaborated to you, and I will go on and apply it to the problem and show you how you can correctly solve the problem using that method that I have explained. So let me commence with reading the problem. The problem starts with a diagram. It has a spring with a rubber plate and a tube and different pinholes as shown here. Let me read the problem. A projectile launcher consists of a spring with an attached plate as shown in figure 1. When the spring is compressed, the plate can be held by a pin in any of three positions A, B, or C. For example, figure 2 shows a steel sphere placed against the plate, which is held in by a pin at position C. The sphere is launched upon release of the pin. So that is the setup. Now I will go into the questions. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. Question A. The student plans to test the hypothesis by launching the sphere using the launcher. State a basic physics principle or law that the student could use in designing the experiment to test the hypothesis. And then question A, part 2, is using the principle or law stated in part A1, determine an expression for the spring constant in terms of the quantities that can be obtained from measurements made with equipment usually found in a school physics laboratory. B. Design an experimental procedure to test the physics in which the student uses the launcher to launch the sphere. Assume equipment usually found in a school physics laboratory is available. In the table below, list the quantities and associated symbols that would be measured in your experiment. Also list the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them in the space just below the table. And then question B continued is, discuss the overall procedure to be used to test the hypothesis of that spring constant of the spring inside the launcher that has the same value for different compression distances, referring to the table. Provide enough detail that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use symbols defined in the table and or include a sample diagram of the setup. So basically it's just asking you to give an elaborate description of how such an experiment that you invent could run. Alright, C. Describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression values. And then question D is, another student uses the launcher to consecutively launch several spheres that have the same diameter but different masses, one after another. Each sphere is launched from position A. Consider each sphere's launch speed, which is the speed the sphere has at the instant it loses contact with the plate. On the axis below, sketch a graph of the launch speed as a function of the sphere mass. So the graph is provided on the edge, on the bottom of question D. So I'm going to give a quick synopsis of what you need to know in order to be able to solve this problem. In order to be able to solve this problem, you need to know what spring force is, what the equation for spring force is. You'll need to be able to understand the concept of work, what the equation for spring work is, and how to set up in an experiment. I will start off with spring force. As you know, force equals ma from the other videos. A force can be applied by any numerous number of things. Basically, a force can be applied by, we've looked at tension, A force can be applied by a frictional force, a force can be applied by a normal force, or a force can be applied by a spring force. And there are also many different other examples and other versions, like the sine theta of a of tension or something. And each of those forces has its own unique equation that can be used to sort of cancel out variables, and that can be replaced for F. Oh, there's also centripetal force. Yeah, so in the spring constant case, in the case with a spring, the force equals ma, but not only does it equal ma, the force also equals kx. This is the equation for a spring, where k is the spring constant. K is a value that doesn't change, and it sort of measures the strength of the spring. As you probably can tell, springs can range in like different values of like how strong they are and how much force they can apply. Obviously, a pencil string or the spring in a pen is not going to be very strong. However, if you took this big bed spring, you're going to feel a lot more force when you compress it. And so basically what that spring constant is it's a number that we're trying to prove doesn't change for a spring the more you compress it, and it's a number that is sort of like proportional to the strength of the spring, how much it's going to apply a force back on you. And then so you have F equals kx, and x is the distance the spring is compressed. So the more you compress a spring, the more force it is going to push back on you. Or when I say distance compressed, I mean distance from the equilibrium point. Every spring has an equilibrium point, and that equilibrium point is the point when the spring is at rest. It is not being compressed at all. It is simply just being pushed with no net forces on it. It has no net forces on it. It is simply just existing. Like if it's lying flat, it has canceling normal force and mg, and there's no force that's going to be pushing or compressing it. So it's going to have a certain distance from one end to the other that is considered its equilibrium point, a point when there is, like I said, no force applied on it. So x is that distance. Now you can feel the force being pushed in. Also, if you pull out a spring, you should feel the same force. Next thing I'm going to talk about is how to set up an experiment, as a big chunk of this FRQ is knowing how to set up an experiment. Question B and question C entirely rely on having that knowledge, and question B and C are both question B is multiple questions, multiple parts, and C is one part. So together they make up a large chunk of the question, half of it basically. So that is a very essential skill for someone to know. And in order to know how to successfully set up an experiment, there must be only one desired variable, and that variable is going to be able to be determined by doing measurements for other variables. Usually you have a dependent variable and an independent variable, and you're trying to look at how the dependent variable changes based on the independent variable. In this case, the dependent variable is the spring constant, and the independent variable is the distance, and the dependent variable is the spring constant, as we're trying to measure if we change this distance of compression, how much does the spring constant change. So when you are creating an experiment, you have to make sure, obviously naturally you're going to have multiple variables, but you have to make sure that you are going to be measuring every variable except one, and every variable except that one that is desired. And you have to be keeping control of you have to have a control variable generally, so you're only changing one variable and you're getting one result. You want to try to keep all variables constant except for one, so you can see how does one thing affect the rate of another. Concept of work is also really important to this problem, as it does come up in question D. It is in fact how you can find the velocity of the object, because work actually relates to kinetic energy, and kinetic energy has velocity in it. which would allow us to solve for that velocity when we know the masses are changing. I will then discuss the concept of how work works with a spring. Yeah, work works. Um, and some of the cool properties it has. So let me begin by explaining the concept of work. Work is defined as force times distance. Um, it is a measurement used in physics. You measure how much work you're putting onto an object by not just the force you apply, but over how long a distance you apply that force. Um, so this is useful as if you are applying a force to something for longer, causing it to move greater. You are doing a different thing that we have defined as work, and work is actually really important when it comes to physics, because work has a very interesting relationship with energy that makes it extremely important. You see, work not only being equal to force times distance, work is also equal to the change in kinetic energy of a system. Um, Although it can also be used for gravitational energy as well, but work can be seen as the change in kinetic energy of a system. And as I was already saying, the kinetic energy can be equal to 1/2 mv squared. Work is in general basically there are things that are called conservative forces versus non-conservative forces, and in a conservative force, um the work that an object does um, is always just the distance from point A to point B times the force that was put in. This means that no matter what path an object takes to get from one distance to the other, whether it goes or whether it goes past and then back around, all those net force vectors are just going to cancel out, and it means that the force is going to be, or the work is going to be the same no matter what path it takes from one direction to the other. This is called the conservative force, and it generally happens when there's no other forces acting on an object that will depend on the distance it travels, such as frictional forces or resistance forces. A non-conventional, whatever you call it, force uh, does it does matter what path you take, and the net work done will not be the same no matter what path you take. It'll change, and this is generally because there is some sort of force that's canceling out the object, or that's adding to the object, that is or some work done that's canceling out the work done in one direction or adding to it, that depends on the distance it travels. Friction is a really good example of this, because say you have something moving forward and back on a frictionless surface. If it moves back, it's going to have done the same amount of work because it's going to move forward, and then so that's going to be a force times the distance, and then it's going to be moving a negative distance back, so that negative distance is going to completely cancel out the forward distance. However, on a surface with friction, there is going to be a force that's constantly opposite the direction that it is going, and therefore the more contact it makes, or the longer it's in contact, the more force there is going to be. So say it goes in a straight line, or if it goes all wiggly, and it does this added distance, it is going to feel more force from the friction pushing back against it. Another example of this, as I said, is air resistance. Something experiences more air resistance if it falls in a non-direct path. The equation for the force for the work done by a spring is relatively similar to the force. The force done by a spring is k times x, and the work done by a spring is 1/2 kx squared. This leads to some interesting patterns. When you are graphing the force on a spring as the distance changes, you find that it increases linearly, right? If you apply a force that's if you change the distance to be twice as large, you're going to experience a force twice as big. This is because it is just multiplied by that single x value. So you're going to have, say if it's 1 meter, k times 1, versus if it's 4 meters, k times 4. So 4k x is, or 4k is 4 times as big as 1k. And therefore you can clearly see that the amount of force you put in, that is going to be like the ratio. If you put in double, you'll receive double. If you put in triple the distance, you'll receive triple the force, etc. However, this is not the same for work with the spring because of the square. This means that if you put in double the force, or double the distance, the work, or the energy it's going to have, because work is related to energy, is actually going to quadruple, as 1 squared is just 1, or 1x squared is just 1, but 2x squared, the whole quantity squared, is equal to 4x squared. So as you can see, if I do the math, say I have x equals 1x, or x equals x, right? And I say the work originally equals kx squared, and then I say x equals 2x, right? Then I have 1/2 k times 2x squared. 2x squared, if I distribute the square root, is going to actually be 1/2 k times 4x squared. And if I call 1/2 kx squared, if I call that a random variable like z or something, you see that you have 1/2 kx times 4 in the second example, which is equal to 4 times z, which means that when you double the distance, you are doing 4 times the work, as when you just have the distance when you don't or you're doing 4 times the work as you double the distance. You'd be doing 9 times the work as you triple the distance, as you have to distribute that square root. Now I'm going to address the laws of conservation of energy, as they're also what allows us to solve problem D. The laws of conservation of energy state that an object in a system will always have the same amount of energy unless there is some non-conservative force, such as friction. If there are no non-conservative forces, it's going to have the same amount of energy no matter where it is. It's just that that energy is not going to be exactly in one form. It can switch forms. So gravity or energy can be seen in multiple forms, but the ones we're most used to working with are potential energy, kinetic energy, and potential energy from a spring. Usually we look at potential energy in terms of gravity, right? mgh or ug, but sometimes we look at it in terms of the spring, as compressing a spring does give the thing potential energy. So as an object moves through a system, say it's dropped down a slide, at the top it's going to have a ton of potential gravitational energy, but it's going to, as it falls, all be converted into kinetic energy so that no energy is lost. The equations for the energy of the three things we're used to working with, gravitational energy, kinetic energy, and spring energy, are, well, for gravity it's mgh equals the energy. This makes sense because it's a force, mg, the force due to gravity, times the distance. So it's also a work, and as we know, work is related to energy. So mgh equals E. The second one is 1/2 mv squared equals E. 1/2 mv squared is the equation for kinetic energy, and then the third one, as I just said, is 1/2 kx squared is equal to, in energy form, a form of potential energy. So say you have a marble or a mass drop from a certain height, you can calculate the total energy it has. It has a gravitational potential energy, and that is going to be its mass times gravity, the value of gravity on Earth, times the height it's dropped. And then you can know that that's all going to be turned into kinetic energy. Now you can add to the situation. If you have a spring, you can say at some point it's going to be dropped and it's going to be pushing the spring back a bit, and it also is going to have kinetic energy, so you know that that work from the initial that energy from the initial height is going to be turned partially into potential spring energy and partially into kinetic energy. So this is going to give us the equation that is so essential for solving one of these problems, which is mgh1 plus 1/2 mv squared 1 v mv1 squared, the first velocity, plus 1/2 kx squared 1 equals mgh2 plus 1/2 mv squared 2 plus 1/2 kx 2 squared. And basically what this is saying is, if you look at the total amount of energy it has at a single point, right, whether that's at the very start or basically anywhere on its path, right, and you break up its energy, you find the three values, you find its total energy, and you can find the three values of energy, then you can say, so basically you can say this value that I have calculated is going to be equal to this, is going to be that the energy that I have received is going to be equal to the energy at any point along its path. So say I know the energy is going to be like 50 joules. That is going to be really important information to me, because if I know a point where all the energy is now kinetic, I can calculate the velocity, or I can know the spring constant if I know it's all going to be the in the spring potential energy form. So usually we start by looking at it when it's all in one energy, usually mgh, although we can look when it's all in one velocity, and then we can easily calculate, although it's easier with mgh because the measurement of height is easy to find and often given. So we can calculate the amount of energy it has at the very start when it's released from its this point, in which case the height would be 1, the v1 would be 0 as it's at rest, and the x1 as it's not on a spring that's not compressed would be 0, so it would be mgh plus 0, and that value is going to tell us the value of the energy that the system has as a whole and will continue to have. So this is going to be really helpful for us when we're trying to solve one of these problems. So I think this is all the science we need to dive into the problem set, so let me commence with that. Now let's revisit question A, part 1. State a basic physics principle or law the student could use in designing an experiment to test the hypothesis. Well, the very first law he can, or a student can use, is that F equals ma and that F also equals kx. So you can set ma equals kx. Now, this is important because we already have two measurable values, right? M and x, right? The acceleration, most physics labs don't really have an accelerometer, so I sort of want to simplify that a bit, but that's already two of the three variables we need to find k. So that is a simple equation we could use to help us solve the problem. Another one could be 2a delta x equals v plus vo squared equals v squared, a simple kinematic equation, because we can get a on itself, by itself, right, subtracting vo squared from both sides. 2a delta x equals v squared minus vo squared, divide by 2 delta x, and you get a equals v squared minus vo squared over 2 delta x. So you can also plug that back in and get m times v squared minus vo squared over 2x equals kx. And we can also know that v squared equals v naught squared equals 0. Vo means v naught, right? As it is going to be starting from rest. So we know that mv squared over 2 delta x equals kx squared, or equals kx. So this is what I have so far. It's just a simple algebraic process. However, now it wants us to, in question A2, determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in a school physics laboratory. So now I'm going to try to get k on its own. We have m times v squared over 2 delta x equals kx. Let's just call delta x x, as it's the same thing. That x is both referring to the distance it's compressed. So let's multiply both sides by 2x, and we get mv squared equals k equals 2k x to the 2kx squared, which is actually looking similar to an equation we already know if you divide by 2. But now I'm going to divide by 2x squared, and I get k equals k is going to equal this equals mv squared over 2x squared. The velocity here, if you don't have a speedometer, right, the velocity can also be measured as the change in distance over time. So it's going to go that certain distance, and the velocity is how fast, or the velocity is how long it takes for it to travel that said distance. So yeah. So if we square that v equaling x over t, we get x squared over t squared. We get mx squared over t squared over 2x squared. So that's going to be equal to mx squared over t times 2x squared. We can cross out the x squareds, and we get k equals m over 2t. I'm going to leave it in the form k equals mv squared over 2x squared, for the reason that the velocity might actually be changing as it goes. So this is sort of just an average velocity that we calculated, and the velocity could really be changing. So I'm going to put that as my answer for A2, and for A1 I'm going to be putting my answer as f equals ma and f equals kx. So now we have all the values we need to measure, right? If we want to know k, we need to know the mass, we need to know the velocity, and we need to know the distance. Or instead of knowing the velocity, we can know the distance and the time. So really we could potentially just need to know the mass, the distance, and the time, which can all be measured. So we have mass, velocity, distance, and time. The units are, the symbols are m, v, x, and t, and the measurements are 1 kilogram or kilograms, meters per second, meters, and seconds. I should mention that when you have simplified k to equal m over 2t, that obviously shows you already that the distance, a bit of a spoiler, but has nothing to do with the value of k, as distance is nowhere in that equation. Now right now you might be thinking, hey, well, before you cancel out that v, right, you have k equals mv squared over 2x squared, and there is still an x in that equation. So wouldn't changing the value of x actually change the value of k, because you're making the denominator bigger? But the answer is actually that is false, because if you look at the equation for energy and you say 1/2 kx squared equals 1/2 mv squared, as you are changing the distance, you are also in fact changing the velocity, or the final velocity that it is going to have. And you can see, since they're both squared, that when you double one of them, you're going to double the other. So actually raising the denominator, if you double the denominator, you're truly just going to double the numerator, and it becomes clear at that point that the x value, that the distance does not matter when determining that k value. So now I'm going to describe an in-depth procedure of how this problem could be solved. I will start by saying we have the k, which we want, we have the mv squared, and the 2 delta x squared. So it could start by having the sphere on the spring. you'd measure how far a student would first take the sphere, put it on the spring, push it back, and set the pin so that the spring would not move. It would get a measured value for the distance. It would, before it did that, or suppose after, if it wanted to take the ball off, the student would measure the mass of the spring. Then the student would get a stopwatch, either a stopwatch or a speedometer, depending on what was available, because both could work. So if the student has a stopwatch, which I assume is more available, the student could look and time the amount of time it takes for the ball to return to that equilibrium point, and then you already have all the values you need if you're using k equals m over 2t. So really that's all that you need, but also if you want to use a speedometer, you would measure the speed it has as it reaches that equilibrium point. So let's write this down into a formal step for part C. So step 1 would be measure the mass of the ball. Step 2, measure the distance the spring is compressed. Spring is compressed. And then step 3 would be carefully release the pin, and then time how long it takes for the carefully release the pin and time the amount of time it takes for the sphere to reach its initial position, or measure the sphere's velocity as it reaches the initial position. So carefully time the pin, carefully release the pin, and time the point where it passes the equilibrium. So there we have problem C. That's the continued version of problem B. And then problem C is describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant spring constant of the spring inside the launcher has the same value for different compression distances. Well, we already did that, but as you can see just through the algebraic manipulation, if you manipulate it enough, the x term completely goes away, and all that matters is the velocity and the time. So when recording that, however, if a student was to do an experiment, the experimental data would confirm this hypothesis, and it could be used to confirm this hypothesis by changing the distance at which the spring was compressed, then measuring the velocity, plugging it into the equation we already found, and see if the number changes. But I already showed that it shouldn't, as the velocity should increase at the same rate as the distance. So now I will talk about the final problem in the FRQ, which is D. So D states, another student uses the launcher to consecutively launch several spheres that have the same diameter but different masses, one after the other. Each sphere is launched from position A. Consider each sphere's launch speed, which is the speed of the other sphere the instant it loses contact with the plate. On the axis below, sketch a graph of the launch speed as a function of the sphere's mass. So basically we want to find out, as the mass changes, how does the velocity change? And we can use that using the work equation. We know that 1/2 mv squared equals 1/2 k, and then the distance it's compressing is a, so 1/2 ka squared. Now, the distance is not going to change, so that's a constant, and the k is a constant, as we already proved. So we have two constants. So these constants can really be anything. You can set them to 1 if it makes it less confusing. But basically, you can cancel out these 1/2s, and you have mv squared equals ka squared. Now I want to see what happens when we increase the mass. So say you have mv squared over Ka squared. So let's first find what V is alone. So V, this is the standard V when the mass is just m. You have V squared equals Ka squared over m, square root it all, and the velocity should equal the square root of Ka squared over m. And these are just two constants, these K and this A. Now, let's see what happens when you increase the mass by a factor of 2. We're going to have 2mv squared, right? That 2 coming from the second mass, equals Ka squared. Now we're going to have to divide by 2m, and we get v squared equals Ka squared over 2m. Square root the whole thing, and v squared equals Ka, the square root of Ka squared over 2m. Now, if we call since the standard velocity we already know is the square root of Ka squared over m, what is the ratio of Ka squared over 2m to Ka squared over m? And the answer is the v squared when you increase, or the velocity when you increase the mass to 2 times its original value is going to be the square root of 1/2 times the original value. Let's check again with mass being 4 times. We're going to have 4 times mv squared equals Ka squared, and divide by 4, mv squared, and 4m. mv squared, or just v squared, equals Ka squared over 4m, square root it all, and we have v equals Ka squared over 4m, all in the square root. So if, once again, Ka squared times m equals x, then the value you'd have to multiply by x to get this would be 1 over the square root of 1/4 times the square root of Ka squared over 4m. So you'd have to multiply by the value of the square root of 1/4, which is the same as 1 over the square root of 4, which equals 1/2. So basically, when you quadruple the mass, you have the velocity. When you double the mass, you are multiplying the velocity by a factor of root 1 over 2. So basically, whenever you increase the mass by a certain number, let's call it a random variable. Let's call it a random variable like r, right? Or let's do s, right? Say you have a random variable s. When you multiply the mass by that much, you're going to change the velocity by 1 over root s. So you're going to be multiplying it by that factor. So it's going to be decreasing, right? It's always going to be less, and the amount it's less by is you're dividing the whole thing by the square root of the number you're adding. So say you're adding 16, the mass is good, it's going to have 1/4 the velocity, as that's the square root of 16. Say you're adding 256, it's going to be 1/16 the velocity. And so I think we can get the pattern now well enough to graph as a function of mass. Okay, so now I have created a graph that represents the relationship of the mass and the velocity. So we know at a mass of 1, the velocity is going to be the constant Ka squared over m, and we know the factor at which it changes when the mass changes, right? When the mass is doubled, it is decreased by a factor of root 2, and when it's quadrupled, it's decreased by a factor of 2 or halved. So we can start by graphing this. I'm skipping straight to 4. We have 1, and it's going to have this constant value. And then when you go to 4, it's going to be half that value. And when you go to 16, it's going to be half of that value. And if you were to keep going, you will see that it's going to keep approaching 0, but the distance. So as you can see from this graph I made, it's going to be approaching 0. I had gotten cut off because I ran out of storage space on the last clip, but yeah, it's going to be approaching 0. And then if you want to graph, mass is going to be halving, right? When the mass halves, it's going to be multiplied by a factor of root 2, and when it's quadrupled, it's going to be doubled. So it's going to follow this pattern as well, and it's going to go up like that and down like that, and that is basically the final answer for the last question. So by now you should fully comprehend what work is, the concept of work in spring force, conservative and non-conservative work, and then also the conservation of energy and how energy relates to work, and how you can set up an equation with energy in order to be able to find the total energy of a system, and then be able to find new variables such as velocity, as we did in problem D. Or if you know velocity, you can find mass, or you can even find the spring constant. Although we use the force equation, you can also use the work equation.